So the question here is, could you derive the stress transformation equations for the 2D stress problem? Let's first define precisely what is it that we want to do here. This picture shows the components of the stress acting on a 2D differential element in the xy plane. We are interested in finding the stresses acting on plane AB, which is inclined to theta to vertical, like shown in this picture. Showing this plane outside the differential element, here is the plane AB, and here are the stresses acting on that plane. We will take this as our x prime axis, and therefore y prime axis will be perpendicular to that, and these are the components of the stresses acting on the y prime plane. So here we seek to establish relationship between stresses acting on the x prime and y prime planes and the stresses acting on the x and y plane in terms of the angle theta. Our approach is to use Newton's law to establish these relationships. In other words, we're going to use the equilibrium equations. As you may recall from statics, utilizing the equilibrium equations requires first identifying the body to be analyzed and then establishing the free body diagram for that body, right? Here the body that I want to analyze is ABC, this little triangle. This is a 2D problem, so we're going to consider a unit length into the paper. So we're going to section this 2D differential element along AB, cut out this triangle, and complete the free body diagram by putting all of the forces acting on that triangle. Here is a picture showing just the stresses. Remember, stresses are not the forces, right? So we need to multiply each of these stress components by the corresponding areas on which they act in order to convert them into forces. That's what I have done over here. In doing so, I have taken the length of side AB as little l. Then, of course, this vertical side AC would be L cosine theta, and the horizontal side BC would be L sine theta. These lengths multiplied by a unit length into the paper gives you the corresponding areas on which these stress components act. That's what is shown in this picture. Now let's consider the picture showing the forces acting on the faces of this triangle ABC. We are interested in establishing equations for sigma x prime and tau xy prime, utilizing the equilibrium equations. Now you can see if I were to write down an equilibrium equations in the x prime axis, only sigma x prime will show up in that equation, not tau xy prime. And therefore, I can easily establish an equation for sigma x prime from that equation. So that's what I have done over here. In other words, I'm summing up the forces over here in the x prime axis. Note that if this is theta, then this angle right here is theta, and then this angle is also theta. The details are pretty easy to follow, but let's go over the details for at least one equation here. Alright, so that's the first one, summing up the forces in the x prime axis. So we have sigma x prime times L acting in the positive x prime axis. Then there's sigma x times L times cosine theta resolved in this direction. So we need to multiply that by another cosine theta to do that. And that will be a force acting in the negative x prime axis. Then we take this force due to the shear stress, which is tau xy times L cosine theta, and resolve that in the same direction. So we need to multiply that by sine theta. That is also going to be in the negative x prime axis. And you do the same thing for these two forces. So the force due to the shear force will be tau xy times L sine theta times cosine theta. Force due to the normal stress sigma y would be sigma y times L times sine theta times sine theta, right? So both of these are acting again in the negative x prime direction. Now you note that L appears in all of the terms, so they could be cancelled. And simplifying the remaining term, we have this expression for sigma x prime. Now you may recall this trigonometric relationship between 2 theta and theta. So utilizing this, we can express each of these trigonometric terms in terms of cosine to theta and sine to thetas. And that's what I have done in this step. And now, simplifying this one more time, we have this equation for sigma x prime. Now we sum up the forces in the y prime axis. Again, the details are easy to follow, so I'll let you follow the detail. We end up having this equation for tau xy prime. Now we need to establish an equation for sigma y prime. We got x prime axis by rotating the x-axis in the counterclockwise direction through an angle of theta, right? Now if I rotate this by another 90 degrees, I'm going to get the y prime axis, the axis that we are interested in, right? And therefore you can see we could derive an equation for sigma y prime simply by replacing theta in the equation for sigma x prime by theta plus 90 degrees. That's exactly what I'm doing over here. I took the equation for sigma x prime but replaced theta by 90 plus theta. Once again, you may recall these trigonometric relations. And using these relations, we get this expression for sigma y prime. Here's a little summary of the three equations. This is the equation for sigma x prime. This is for sigma y prime, and this is for tau xy prime. Here is a slightly more compact form, and here we define three different parameters. The first one we will call sigma average. Sigma average is sigma x plus sigma y over 2. And then the second parameter, little a, which is sigma x minus sigma y over 2. And the third parameter is little b, which is tau xy. In terms of these three parameters, these are the three equations that we are interested in. An important aspect to be kept in mind when using these equations has to do with the sign convention. This is the sign convention used in deriving these equations. Sigma x and sigma y are positive if tensile. Tau xy is positive if counterclockwise on the x-plane, which is this plane right here. And theta has to be measured from the positive x-axis in the counterclockwise direction. If it's measured in the clockwise direction, that will be a negative number.